Hello, my name is Antonio Cobarrubia. I'm a PhD student in the Computational Science program, working with Dr. Sanjay Bahura, Quantum Materials Lab at San Diego State University. Here I'll be talking about quantum control qubits and hexagonal boron nitride quantum defects. Quantum materials have been an emerging technology in quantum information science due to their abilities to be qubits for quantum computers, quantum sensing, and quantum networking. The advantage of these quantum materials is that they're able to emit single photons, which can then be encoded as a qubit. One of the most popular examples of these quantum materials is the nitrogen vacancy color center in diamond, which is able to showcase single photons at cryogenic temperatures. However, in the case of hexagonal boron nitride, or HBN for short, it's able to showcase single photon emissions at room temperature, which due to its large bandgap energy. This is advantageous because we can create photonic qubits at room temperature. HBN hosts a variety of different quantum defects. However, in particular, a negatively charged boron vacancy color center has been experimentally shown to be a stable spin-1 system. This is important because its spin states are able to create a computational state and therefore a qubit itself, much like the case in nitrogen vacancy in diamond. However, to generate the single photon, or in particular these encoded single photon emissions, is not well understood. And thus here we want to simulate and model on the single photon emissions based on the spin properties of the VB minus defect. Therefore, incorporating its Hamiltonian of this defect and the transition due to an excitation from a laser onto this defect, we want to model this transition time from the ground state to excited state while incorporating a metastable spin zero state transitions as well. From the energy transitions described by the spin-1 Hamiltonian, we can develop a lambda-like model to showcase the quantum control of these single photon emissions. And this is where we modified the lambda-like transitions to incorporate horizontal and vertical encoding. This is done through an input field, or our pulse, exciting the ground horizontal and vertical modes into an excited state, such that the transition from the excited to the horizontal and vertical ground states is able to create that encoded polarized qubit states. Also incorporating the effects on how the metastable spin zero transitions affects our qubit as well. We then extend our lambda-like model into a quantum input-output network theory treatment to incorporate a pulse HBN SLH triple. This is done so that we can incorporate the source and the HBN SLH triples can be modified together through equivalent SLH rules, where we have a modified scattering matrix, which describes the modified relationships between the input and output field, the modified Lombardian factors, which describes how the field affects the noise of our HBN, and the modified Hamiltonian description, which therefore affects our modified lambda model due to the influence of our pulse input field. Now we want to see how quantum control schemes directly impact the state of our qubit. By assuming a circularly polarized qubit that's being emitted and a Gaussian-shaped pulse, we look at the G2 characterization, which describes single photon emission if it's less than 0.5 over the width of our Gauss. By varying over the width of our Gauss, we see a general exponential trend that appears on average, such that when we have smaller pulse widths, we do see the encoded qubit being emitted from our HBN defects. Therefore, in order to get quantum information out of our VB minus defect, we have to look at the quantum control scheme protocols. Thank you for listening.